Well, hello. My name's Professor Alan Fitzsimmons. I'm a lecturer and a scientist here in the School of Maths and Physics at Queen's University Belfast, and I'm going to tell you today about our physics degrees at Queen's University. Now, this is addressed primarily to students who are thinking of applying to us in the coming year through UCAS or sorry, Claire, I'm going to start that again. Sorry, that was stupid. Let me just carry on. It's weird not having an audience.
Okay. Yes, no problem. Take your time. You can stop and restart whenever you like. It's fine.
Sure. Now, with this will beat the take. Okay. Well, hello. My name's Professor Alan Fitzsimmons, and I'm going to talk to you today about physics degrees at Queen's University. I'm a member of staff here. I teach and I also do scientific research. And as such, I want to introduce you to some of the wonderful things you can learn while you do a physics degree here at Queen's, and also what the structure of the course is. Now, this is a talk that's primarily addressed to people that are applying to do a degree with us next September. But perhaps you're also watching this as an interesting parent and so on. So what I thought I'd do is I'd remind everybody what physics is. Physics is how we explain how our world and how our universe works. It's one of the fundamental sciences that we learn about in school. Now, one important thing about physics is that we found through our investigations and discoveries that quite often we can simplify all the complex things that happen around us to some very straightforward, generally mathematically based laws of nature. And so this is what is meant by this quote from Jocelyn Bell Burnell, who was a Queen's alumni, of course, and is one of the famous discoverers of neutron stars or pulsars in our universe. As she said, you can see, you don't have to learn lots and lots of facts. You just have to learn a few key things. Then you can apply and build and develop from those. Well, if you were in the middle of doing your A-levels in physics, that may not sound quite what you're doing, because you are learning a lot of facts. You are learning a lot of things in different areas, but they all tend to have this general process of learning a mathematical law, which is a law of nature, then applying it to explain what we see in the world around us. So, for example, the backdrop here is an image of a remote galaxy, rather like our own Milky Way. Through physics, we know that our sun is just one of 100,000 million stars in the Milky Way, and the Milky Way is something that we can investigate using telescopes, which in turn use optics in physics. We detect the light from those galaxies using things called CCD cameras, which use the quantum physics that we now know about, and all this comes together. And so, although there may be very simple fundamental cores to all of physics, they spread out into many, many different areas. And again, some of these areas you will have learnt about or been introduced to at school. Physics involves forces, it involves energy, it involves understanding the structure of solids, liquids, gases. It involves how atoms behave and how you can put those atoms together to form molecules. It involves light, radio waves, another form of light. It involves X-rays, another form of light. It also involves particles, a different type of radiation. And of course, light and radio waves, we learn to control and apply through the forces of electricity and magnetism. Now, all of this might sound kind of general and so on, but there are real applications to physics. So one thing that we can do now in physics, and you can see this on the left-hand side of this slide, is that we can take optical devices, microscopes, and zoom in to a certain level to look at structures on the microscopic level in surfaces and in materials that we can create in laboratories. And then using highly advanced microscopes, things that use quantum physics, we can go down to the level of individual atoms, and we can see individual carbon atoms, for example, as we can see in the lower right-hand image here. And doing that, physicists in laboratories around the world are now working on flexible displays, flexible designs. In perhaps 10, 20, maybe 30 years' time, we'll be able to roll up our smartphone and put it in our pocket. So these have physics has tremendous applications for practical day-to-day use. It also has important applications for our society and how we live on our planet. We know that our planet is undergoing global warming, and it's doing that because of the release of carbon into the atmosphere. And so we need to stop doing that. But we need to have other forms of energy generation. And now, these days, we're all familiar with the large wind farms we have both on land and at sea. Now, the way we can extract energy from wind or from tides or from geothermal energy involves at its heart physics. For example, one thing you'll find out when you do a physics degree is that there's a limit to the efficiency with which you can extract energy. There is a fundamental limit baked into the laws of nature in our universe, which tells us we can never design something like a windmill and take 100% of the energy in wind and then convert it to electricity. And understanding those limits and how to approach those limits is something that physics is all about. Applications of physics, of course, also does go into what you might call blue sky research, or even dark sky research. Over the past 20 or 30 years, astrophysicists, such as myself, have investigated how stars are formed, how planets are born. And over the past 3 decades, we've gone from a situation where we only knew of the planets in our own solar system going around our star, the sun, to knowing of literally thousands of other planetary systems out there in the nearby universe, some of which may have planets that are habitable. We're still working on that, and that's part of research in physics, taking what you know and pushing it forward. And we can go, of course, in physics research from the very large to the very small. This is a picture of the world's largest machine at the moment. This is one of the 3 main detectors at the Large Hadron Collider, buried underground in Switzerland, 27 kilometers across. This is the machine that physicists use to understand the fundamental structure, not only of atoms, but the particles within atoms, and trying to understand how our universe is put together and everything in it at the most deepest level. So all of this is physics, and all of these physics fields that I've shown you pictures of, you'd be at least introduced to within the School of Mathematics and Physics at Queen's. Now, if you look at physics at Queen's University, there are 36 academic staff, such as myself, staff that are employed not only to do research, but also to teach. We have 32 research fellows. These are non-permanent physicists that are employed to show us, or help us, I should say, understand the physics we are researching. We have 105 at the moment physics PhD students. These are the students that have already got a physics degree and have carried on to try to earn their doctorate in physics. And we also now, at the moment, have another 250 undergraduates studying physics with us, attempting to get their degree with us. And it's only 250 because right now we've just graduated our class of 2020. So when the new physics students start in a month or so's time, that number will increase by about another 60 straight physics students and another 30 joint students taking applied maths and physics or theoretical physics degrees, as we'll see, which combine mathematics and physics together. Now, when you come and apply to do a physics degree with us. There are many different types of physics degree. First of all, we have, again, what we call the main physics degrees. Physics, physics with astrophysics, physics with medical applications, or physics with French or Spanish. And these are the degrees where you will spend a lot of your time, not all of it, but a lot of your time doing physics. Then we also offer what we call joint degrees within the school. These are degrees aimed at students who are not sure what they prefer, whether they prefer physics or they prefer mathematics, in which case what we do is we allow them to study both at the same time. So we offer physics and mathematics degrees, these joint degrees, and these come in two flavors: theoretical physics or applied mathematics and physics. Now, don't think that if you just do the straight physics degrees, you will not be doing any mathematics. You will indeed, because the mathematics you do at A level is not enough to do a physics degree. We need to take what you've learned at A level and enhance your understanding and extend it so that you are fully equipped to handle mathematics in areas such as quantum physics and solid state physics and astrophysics. And because of the degree of learning that you'll be embarking upon in a physics degree, then our entrance requirements are relatively high, as you'd find for any other physics degree in a Russell Group university. Now, apart from those subjects, that we have two different lengths of degree that you can do. And first of all, we have the traditional Bachelor of Science, the 3-year degree, for students who enjoy physics and will take their physics skills and the skills they learn into various careers. Our requirements for this is that if you're doing a straight degree, our entry grades are A and 2Bs, and those A levels must include mathematics and physics, but honestly, the third one we really don't mind about. For the joint degrees at BSc, the applied mathematics and physics degrees, we ask for 2 A's and a B, and one of those A's must be in mathematics, and that's because of the high mathematical content in that degree. Now, for students who want to study with us a little bit longer and really want to get to the edge of understanding in physics and perhaps are considering carrying on afterwards to a postgraduate degree, then we offer the 4-year MSci degrees. These are students who really are contemplating or might want to leave their options open to a postgraduate work in physics. And for these degrees, we require 3 A's. And again, this is both for physics now and for the joint degrees in mathematics and physics. So one thing one students ask me a lot is that you've got these two choices. How many students do we have in these degrees? And it's almost exactly 50-50 normally. We have about half of our students taking the 3-year degree and half taking the 4-year degree. Both of these degrees are good honours degrees in physics, and importantly, for the first 2 years, they are exactly the same. And so we have just a single large class in all of our physics courses or physics modules, whereby everybody's learning the same physics in the first 2 years. Where will you be learning these degrees? Well, we are the largest academic school on the main central campus around the Lanyon building. We have, first of all, a teaching centre for mathematics and physics just in front of the library, which contains 4 lecture theatres, 4 seminar rooms and small lecture rooms, 2 student physics suites. It contains all our physics laboratories for teaching physics and some staff offices. We also have the main physics building as well, just between between University Road and the Lanyon building. And this houses most of the rest of the staff offices, plus the research labs, which some students will get to see and work in during their 4th year if they take the MSci option in their physics degrees. It's pretty good. It's close to the library, it's close to the student union, it's close to all the eateries. We're pretty happy with where we are. So this is where you'd be taught in your physics degree. What are you taught? Well, this is the general course structure for the straight physics degrees. And for example, if you concentrate on the first year, you would have two modules, or an equivalent double module in physics, the same amount of teaching mathematics. Remember what I said, that we'll need to bring you up to speed with the mathematics you need to learn all of the advanced physics you get to encounter in your degrees. We also give you a course on computer programming, because most of our students have not done any computer programming before, and we need to start you from basically step one so that you can apply that computer programming. It also looks pretty good, by the way, on the CV. And of course, because you're doing physics, you'll be doing experiments and also learning about data analysis. And that's crucial for physics, because physics is an experimentally based subject. We can sit in as many lectures and read as many textbooks as we like, but you need to know how experiments are performed and how data is handled and how we perform those calculations to match our theories to the experiments to know that what physics we're teaching you is actually correct. And hopefully, perhaps in the future, you'll go on to perform your own experiments or match your own theories to the data. Then in second year, you'll see it start specializing in individual physics modules, quantum and statistical physics, for example, where we start learning how to calculate wave functions with the quantum waves that form the basis of all atoms. Solid state physics is how we put atoms together to form the structures we see around us in the world on our planet. Electromagnetism, of course, brings together the theories of electricity and magnetism into one unified fundamental force of electromagnetism, one of only 4 fundamental forces we've found so far acting in our universe. Then we've got Astrophysics 1, where we introduce you to what's there beyond our atmosphere, the rest of our universe. You'll get atomic and nuclear physics, where you take the material you've learned in quantum and statistical physics and see how we use that to learn both how atoms interact and how what the structure is of the nucleus. And together with that, there'll be a little bit more mathematical physics just to keep you on your toes in terms of understanding this material. Then in level 3 and level 4, year 3 and year 4, what you do will depend on your degree. If you're doing the BSc, you will do a bunch of modules in physics, continuing your studies in there, but also you will do 2 one-semester projects in your final year. If you're doing the MSci degree, the 4-year degree, you'll get a final year project in year 4, which will be your final year. And in that project, you will be working within one of the research centres here in physics at Queen's. Now, this is how the courses have been traditionally structured. We now, of course, offer placements in our physics degrees, as we do in all degrees throughout the university. And this is an optional extra year between the 2nd and 3rd years of study. You don't need to do it if you don't want to, but if you do, we'll give you an extra skills course, which doesn't involve a lot of work, but just gets you up to speed in terms of preparing for job interviews, writing your CV, etc. And then we give you support in applying for those placements. If you're not successful, because there will be, we believe, quite a call for these placements, then you will just continue with your course as normal. But if not, then you will go and work in a local industry for a year. You'll be paid a wage, and because you're being paid a wage but are still registered as a student at Queen's, you will have to pay a student fee for that year, but it is significantly lower than the normal student fee, so that shouldn't be too much of a financial burden. But it's not up to us, I should say, about how much you're paid. It's the company that decides the salary. Now, I've gone through very quickly the structure of the degree courses and what might happen if you go on a placement. It's not all work. Here's some pictures from our Physics and Mathematics Society, run by the students in one of their recent formals, and you can tell that, you know, students do have a good time. Most of our students have a good time, and they do enjoy themselves. But every student has to sit down and try to work through difficult stuff at times, and that may be due to, from the actual course, or it may be external factors. So I just want to add a point here that we have a tremendous amount of student support within Queen's, and particularly within the school. When you start your degree with us, you'll be assigned a member of staff as a personal tutor who will certainly take a great deal of interest in your progress in your first year and give you any advice and any encouragement and any assistance you might need. You'll also have an advisor of studies, another member of staff that will help you guide you through your choices of your modules and even the kind of degree that you're doing, or the title of the degree you're doing. And of course, every day you'll encounter the lecturers and demonstrators, often other students, sometimes postgraduate students that have been through the degree here at Queen's, to get that on hand to help you out with questions and any problems you might have. Within, outside the School of Mathematics and Physics, we have halls of residence activities for students that are staying in Queen's Elms, but we also have student guidance and student counselling, which are always on hand 24 hours a day to help any students with any issues that they may come up against. Now, I don't want to infer that this is a usual instance. Most of our students don't need to avail themselves of these, but if you do, they're there. And we think overall, we're pretty successful in getting students through their degrees. If we look at our first year progression rate, for example, 95% of our students get through their first year exams and into second year, and the progression rates are similar in other years as well. If you look at our final degree results, then 80% roughly of our students get first class and upper second class degrees, the top two tiers of degree you can get. And remember, these are honours degrees from a Russell Group university, so they stand you in good stead. Now, we don't have the figures for this year yet, but from last year's National Student Survey, 87% of students in physics were satisfied with their degree in the BSc, for example, as opposed slightly higher than the Queen's on average, but it did pretty well. And you can tell that, you know, because this is the end goal, right? You want to get a degree to use whichever way you want in the future. Can't guarantee you'll graduate with a Nobel Prize winner such as Peter Higgs here, but we do guarantee that if you manage to understand the material and you study along with your other students, you will end up with a good degree. So what are you going to do with this degree? Well, hopefully you're going to earn some money. Now, here's an interesting fact. The average graduate salary last year for all students in all UK universities across all degree subjects was £23,000 a year. Sounds pretty good. The average physics graduate salary was over £3,000 a year more. Why is that? Why does somebody working in a bank, perhaps if you've gone into finance or in management, or working with lasers in the medical industry, why do they care if you can calculate the temperature at the core of the sun? Or why do they care if you can derive the equations that allow you to figure out the age of the universe? Well, the answer is they don't, probably. But what they actually care about is that in a physics degree, like many other degrees, it must be said, but particularly in physics degrees, you can do two things. You've learned two core skills. You've learned how to solve problems, and you're numerate. You can use a calculator or indeed a computer. And those two core skills on anybody's CV when they apply for positions in companies means that they're pretty near the top of the pile quite often, particularly if you've got, as I said, a degree from us. So that's why on average, physics students earn more than the average in the entire body of students. It's something to think about while hopefully you're enjoying your degree. Now, the final thing I want to talk about is that in Queen's, we believe there's a strong link between teaching and research. If a student is good enough, they could just sit with the textbook and learn it from the textbook, although that is pretty tough, let me tell you. But the important thing is that all of your lecturers in physics at Queen's are internationally ranked and world-leading scientists. In fact, in the last government assessment of all departments teaching subjects in all universities in the UK, Queen's physics was third in research intensity in the UK, i.e. we had more staff doing more great things on the international world stage than almost any other UK university. And that's because when we teach you, yeah, we're going to teach you what's in the textbooks and show you how to understand it and show you where the frontiers of knowledge are. But we can do that because we're doing the research ourselves. So when we're not teaching you, this is an important thing to remember, we're doing scientific discoveries in Queen's. So for example, we have a 20 terawatt laser in the basement of the physics department, one of the most powerful lasers belonging to any individual university in the world, let alone the UK. We also have a facility whereby we're designing the new materials that are going to future electronics from the atom and the molecule up, designing them so they have exactly the right physical properties in terms of magnetic properties and electrical conductance and so on. And we do that, as I said, from the atom and the molecule up, and then build those structures and build those materials to test them experimentally. Sometimes we want to probe those materials and we don't have the facilities here, so we'd use material or facilities outside Queen's. For example, this is a picture of the diamond synchrotron, where we accelerate electrons in Oxfordshire to almost the speed of light, and in doing so we create the most intense beams of light almost anywhere on our planet. And using those beams of light, we can probe objects down to the subatomic level. We also have staff working on energy generation for the future, in particular fusion reactors. We're not there yet. Fusion is a very difficult job, but here's a picture of the reactor, the test reactor that most of the scientists of Queen's have worked on in the past 20 years, the jet fusion reactor, also in the UK. On the left-hand side, you can see the reactor when there's nothing in it apart from air. On the right-hand side, it's been evacuated, and now we have a plasma at 100 million degrees producing energy. And those lessons are going forward to the next reactor at the moment under construction in France. We also have people like myself. I'm a professor of astrophysics, and sometimes when I'm not there or your other lecturers aren't around in Queen's, it's because we're here. They're over 9,000 feet in the Atacama Desert with the world's largest telescopes, using them to probe what's out there and using the physics that we've learned here on Earth to understand what's out there. And this is happening all the time. So here's a screenshot from today from Physics News, and these are just some of the results announced in the past week or even in the past few days from physicists around the world, just pushing the boundaries of knowledge. And that's what's great about physics. Well, sure, you're going to learn from textbooks. Some of the material you'll learn will be 100 years old in terms of quantum physics and its foundations. Some will be 50 years old. Some will be results that have only been found out in the past year. And that's the beauty of physics. It's always developing and there's always stuff to learn. So I'm going to finish by saying good luck with your studies. If you need to contact us about anything beyond the University Open Days, please email us at this address, mp@qb.ac.uk. And hopefully next September, I'll see some of you in my first year lectures where we'll start looking at the very basics. What's force? What is energy? How are they connected? And how do we use them to understand our universe? Cheerio for now.